Hey ladies and gentlemen, and welcome back to the second part of our 3.3 video lesson on transforming to achieve linearity. So if you remember in part one, we talked about how this concept transforming means to change. What we're doing is we are taking a set of data that is non-linear by nature and we are transforming it somehow mathematically in order to make the data linear. And so the first type of nonlinear relationship we learned about yesterday was called exponential growth. Could also be decay if the values are decreasing as x goes up. And in exponential growth, it's a relationship between x and y based on repeated multiplication. So the exponential function is y equals a times b to the x, where a is our initial value, what are we starting with, and b is our scalar multiple, what are we multiplying by each time. Now, exponential growth is going to have a curved pattern in which the numbers increase very slowly in the beginning and then curve upward and accelerate very quickly, whereas exponential decay is going to drop very quickly and then curve out or balance out and flatten out at the end. So it is non-linear. In order to transform exponential growth into something that is linear, our rule is that we take the log or the natural log of the y values. And you'll see this written as x versus the log of y or x versus the natural log of y. Long story short, when we took the log of the y values, we saw in yesterday's video lesson that our scatter plot went from being curved in nature to linear. So that was our rule. Then we also talked about how the calculator has this exponential model option where you go slide over to the calculate tab, and then option 0 was exponential regression. And it gave us the a and the b values in this form, y equals a times b to the x. And we just had to substitute our values in as well as define what our variables are. Okay, now we're going to move on to example 3 here. This may or may not be true or based off of a true story. I'll just let you decide if you want to go with that or not. Mr. Voss bought a pair of $360 noise-canceling headphones. Knowing his wife would be livid when she found out how much they cost, he needed a plan to soften the blow. He justified that every time he wears them, the cost per use continues to drop. In fact, if he were to wear them each day for 1 month, it would equate to $12 per day. The table shows the cost of the headphones per day. So you can see the first day that I wear them, it's $360 per use. But after 2 times or 2 days, it's $180 a day. And then after using them for 3 days, that would be $120. All we're doing is we're taking 360 divided by the number of days to acquire these new values. Okay, so it says to make a scatter plot of the data. Is it linear? So if you want to make this scatter plot, you can. If you want to just watch really quickly on the calculator of mine, we can do that as well. So one cool thing that our calculator can do is you can see that my list 1 here has all of our days 1 through 30, and I left day 2 or L2 blank. This is our cost. Now, we said that the way we were going to calculate this was by doing 360 divided by the number of days. So what we'll do is this. Hit enter, list 2 equals. List 2 is going to equal 360 divided by list 1. And when I press enter, we can see that that all gets filled in for us all at once. So I don't have to worry about individually typing each one. And we can see again, after 30 days, $12, all of those things are good there. Okay, so it asks us to make a scatter plot. So if I turn my scatter plot on for lists 1 and 2, and then zoom 9, we can see this graph here. And hopefully we can see very quickly that this is a non-linear relationship. Okay, it's dropping down very quickly, and then it flattens out. So more than likely, this looks like it's going to be exponential decay. right? So make the scatter plot. Scatter plot look like this. So is it linear? It is non-linear. So what was our rule? We take the log of the y values in order to achieve linearity. So I'm going to go back, stat, edit, list 2. I'm going to fill in with the log of list 2. Got all my new values there. And then now when I make my scatter plot, what you'll notice is that it's still nonlinear. Okay, in fact, it doesn't look all that different than what we had before. Still looks kind of like this. So, what do? Because when we had x versus y, just our original x and y values, we saw that it was nonlinear. Now, we did the trick that we were taught. Take the log of the y values. My x values stayed the same. Y values I took the log of. But once again, still nonlinear. So, what do? Okay, or what does this mean? The next type of model we are going to learn about is something called a power model. A power model is a function in which the variable is raised to a numeric power. So x squared is what we know as quadratic. X cubed, x to the third is what we call cubic. X to the fourth is what we call quartic. So if we have x to any sort of given power, this is what we call a power model. So the form of a power model, and this should have a y hat equals in front of it. So it's going to be y hat equals a times x to the p. Now, in order to produce a linear relationship from a power model, right, x versus y was no good. X versus log of y was no good. We're going to apply the log to both x and y. We're going to apply the log to both x and y. So now when I go back to my data here, list 1 I'm going to clear out, and I'm going to call it the log of list 1. Now you can see none of my data is the original data from list 1 and list 2. But if I now zoom 9, we can see very, very clearly that this data is now linear in nature. So we've transformed our data in order to make it linear. So for a power model, it's going to be log of x versus log of y, or natural log of x versus natural log of y. Okay, that's just going to kind of be another rule to remember. Linear, x versus y. Exponential, x versus log of y, or x versus natural log of y. That's how we transform it. If it's a power model, we won't get a linear scatter plot until we've taken the log or the natural log of both. But it does need to be consistent. I can't take the log of one and the natural log of the other. We want to make sure we keep the same bases. Okay, so we're going to hold off on part C for right now. Perhaps we can do that another day. But in part D, it says use the model to determine how much the cost per day of the headphones would be after 270 days. So what we've done is we've now determined it's not linear from the first scatter plot. It's not going to be exponential based on the second scatter plot after we took the log of the y's. So it's going to be a power model. We achieved linearity when we took the log of both x and y. So what we're going to do here is go to our calculator, and I'm going to reset my data. So the way we did that is, remember to undo the logs. We just second log. In other words, we raise it to the 10th power. That's what we're actually doing mathematically. So second log list 1 gets all my original data back. And then second log list 2 gets my original data back. And if we go stat calc, right, option 8 was linear regression. Option 0 was exponential regression. Option A, power regression for list 1 and list 2. And I can see my form of y equals a times x to the b. Y hat equals a times x to the b. But y hat can be replaced with cost per day. And that's going to equal the a value, we were told 360, times x, which is the number of days, to the b, which we can see from our calculator, is -1. So there's the equation that we will use in order to predict, or in this case, truly calculate what that would be. Therefore, that's going to be 360 times number of days, 270, to the -1. 360 times 270 to the -1 is 1.3 repeating. And since we're talking cost, $1.33 is the cost per day after 270 days. All right. So here's basically our summary broken down. In order to determine which is best, so we've already done this. You've transformation with powers, roots, logarithms to create linear models, okay? And then make predictions. We've done that. Now, determine which of several models is the best. Okay, which one does the better job? Which one does the best job? So there's the long way and the quick way. The long way is what we've kind of done to initiate or set all of this up. Check for linearity first by using a residual plot. Make a scatter plot of x versus y. And just see, is it linear? If it is, a linear model is best. If it's nonlinear, we scratch it, and then we do this. If nonlinear, take the log of the y values. Check for linearity again. Okay, and if the log of the y values produced linearity, then we know it's an exponential model. But then if that didn't work, now we have to take the log of the x's as well. So log of x's and log of y's. If that produces linearity, now we know it's a power model. If log of x and log of I or log of y don't work, then we don't know. Okay, that's going to be beyond the scope of this course. Okay, so this is a long way to do it. Check for linear first. If it's not linear, take the log of your y's to check for exponential. If it's not exponential, take the log of your x's. It's a model or a power model. The faster way to do this is to just check the linear, exponential, and power regressions on your calculator and choose the one that has the strongest correlation or the strongest R value. Now, one thing that we've mentioned numerous times is that correlation only works for linear relationships. So when we calculate the linear regression, which is option 8, we're going to get a correlation. When we calculate exponential, which is option 0, it's going to give you a correlation, but the correlation it's giving us isn't for the exponential growth itself, but rather after we transformed it to linearity, what is the correlation of that linear relationship? Same thing here. Power regression is option A. When you go to StatCalc, it's not telling you the correlation of a power model because correlation is only for linear. The correlation, or the R that it's telling you, is after you were to transform it, what would that correlation be once we made it linear? Okay, so what we'll do is I'll just show you how to do this through an example, and we will call it a day. Okay, but this is going to be the method we want to use. This way we don't have to actually transform our data and redo it, undo it, all that stuff. It's just put the data into list 1 and list 2, check linear, write down the regression, or write down the R value, the correlation. Then check exponential, write down the R value, check power, write down the R value. Whichever one has the strongest correlation is the best option. Okay, so example 4 here, the distance in astronomical units each planet is from the sun and the time period in years that it takes to revolve around the sun are given below. So we've got each of our planets. How far is it in terms of astronomical units? 1 astronomical unit is the distance from Earth to the sun. So this 0.387 means that Mercury is about 38% of the distance from the Earth to the sun in terms of its distance from the sun. Year, or the period in terms of years, how long does it take that planet to make 1 full revolution around the Earth, or around the sun? So the Earth takes exactly 1 year, whereas Mercury takes about a quarter of a year. So about 3 months, it's gone 1 time around. Whereas Saturn here takes almost 29 and a half years to go 1 time around the sun. So in part A, determine which model would be best to use to describe the relationship between the planet's distance from the sun and the amount of time it takes to revolve around the sun. Justify your answer. So the first part, determine which model is best. Well, my options are linear. My options are exponential and power. So I've got this data, again, just trying to work a little bit faster here. I've got this data here into list 3 and list 4. So what I'm going to do is I'm going to stat calc option 8, linear regression of list 3 and list 4. Now, I'm not going to write out the equation yet. I'm just going to write down the R value. How strong is this in terms of a linear relationship? 0.9881. Okay, so that is extremely strong. Remember that 1 is perfect. So right now I've got this inclination that it's going to be a linear relationship because that's going to be really tough to beat. But I have to check them all. So stat calc option 0 is my exponential model, and I'll take that for list 3 and list 4. And I get 0.895, which is still a strong correlation, but it's not as strong as linear. And lastly, I check my power, which is option A. And I want to do that for list 3 and list 4. 0.99, so practically 1. Okay, there are quite a few of those. Therefore, and actually there's one thing I should do for all of these. R equals, R equals, R equals. So when I look to see which one has the strongest correlation, this one right here has an R value closest to 1, or an absolute value closest to 1. So we would say a power model is best because it has the strongest correlation. That's how we can determine which is best. Just check the 3 correlations, one for each model, and select the strongest one. So now that we've determined that the power model is best, use the model selected in part A to determine approximately how long it takes Pluto to complete one full revolution around the sun if it is 39.529 astronomical units away from the sun. So, because we said that a power model was best, we're going to recalculate that power model for list 3 and list 4. And I'm just going to write out the form that the calculator gives me, which is y equals ax to the b. But I'm going to modify this. Remember that it's y is our period in years. So the predicted amount of time it's going to take is equal to a, which we can see is just 1.000. Okay, so 1.0 times x, which is astronomical units, to the 1.5, which is my b value. Now that I have that, I'm going to take this astronomical units of Pluto, drop that in right here. So the predicted amount of time it's going to take Pluto to make one lap around the sun can be found using this calculation. 1 times 39.529 to the 1.5, which essentially I don't need that 1 times, but I'll put it in anyways. 1 times 39.529 to the 1.5. And we can see that it would take 248.5 years. And that's how we would go about a problem like this. So, one more time, just as a quick review of this entire section. Linear relationships are great, but not every relationship is linear. So we have to figure out ways or know ways that we can take something that's nonlinear and make it linear, and how we can work with that. So the first thing that we learned about is an exponential model. Exponential models are going to have the relationship of x versus the log of y, or x versus the natural log of y. That's how we change our data to make a nonlinear relationship that follows an exponential model linear. And if taking the log of the y's doesn't work, we take the log of the x's and the y's, and if that produces a linear scatter plot, that's what we deem to be a power model. The way we can find these on our calculator: stat calc, option 8, option 0, option A. Write down what are the 3 corresponding correlations for those. The one whose absolute value is closest to 1 has the strongest relationship. That's how we can determine which one is best. Once we do, we use the layout from the calculator with that equation by defining the variables and plugging in the numbers given to us in order to make predictions. Okay. As always, if you have any questions, please reach out, and I'll be happy to help out in any way I can. Otherwise, I'll catch you next time. Thanks for watching, everybody.